Okay, so let's spend some time talking about this projectile motion stuff, because that will be on the final, okay? So basically, there's two types of problems. So if you look on the first problem on number one. So here's this cliff, okay? And here's the carrot car, and you're gonna go flying off the cliff. So all problems that are projectile motion only are one of two things. It's either a lemming problem, where the only velocity that you have is in the horizontal direction, or I have to give you the launch angle and the velocity, and then you have a Vy, and then you have a Vx, okay? So unless I specifically give you an angle, like for example on number 3, in this situation, you're just driving off a cliff, okay? Now, if there was a ramp, whoa. Speaking of driving off a cliff, so if it had hit a ramp and gone flying up, then I'd have to say, oh, here's the angle of the ramp. It's taking off at 30 degrees, whatever it is, okay? So on number 1, it's Vx. So here's the bigger idea. Why didn't I give you the mass of the car? Look on every problem on this sheet, every projectile motion problem that you've had. Why did I not give you the mass of the object? Doesn't matter, okay? There is no way to plug the mass of the object into these equations if you tried, okay? It's not there. Here's the other thing. You have two situations. Situation number 1, I'm going to drop the car and it's going to fall straight down. Situation number 2, I'm going to shoot the car off the cliff like this. What you have to understand is that both of those are going to land at the same time. And here's the reason why. If you look at the equation, the distance equals 1/2 at squared plus v naught time, and your mantra is that what happens in the x stays in the x, and what happens in the y stays in the y. So if you're going to try and use an acceleration of 9.8 meters per second squared, which is important, I'm not discounting that, but you could, that acceleration is only going to impact the vertical motion, okay? The gravity mafia has no influence on the horizontal motion. So your Vx is going to remain constant. That's the key assumption. So basically, even if you look at this equation, there's no horizontal acceleration. This drops out of it. You have velocity times time, which is a fancy, so we just repackage this equation horizontally and we get fancy and we go, oh, range equals Vx time. So if you get a problem like this, take the time, make a sketch and go, oh, right, this thing is 18.8 meters tall. Okay, that's kind of cool. And then it's going to land out here 24.6 meters away. Start with this. Get a visual about what's taking place in the problem. Because if you don't know what's the x and y, you're dead in the water. Okay? You are dead in the water if you don't know what is your x component and what is your y component. So, here's the main idea. I drop a car, it falls straight down. I shoot the car off the cliff, it's going to land out here. They are both going to land at the same time because your Vx is not going to influence at all what's going to happen. Just like if I shot a car off the cliff that had twice as much mass as the first car, but as long as I launched it at the same velocity, everything would stay the same. So you have to look at what is a factor and what is not a factor. So on this one, if I dropped it straight down or if I shot it, you know this equation, distance equals 1/2 at squared. So as soon as you realize, oh, I'm going to be dealing with my vertical distance, this part of the equation drops out. I don't have to worry about it. You know how far it falls. You know 2d over a, the square root of that is going to get you time. And then once you get time, then you're going to know that, you know how far it falls, find your Vx. So on problem number 1, that velocity should be around between 10 and 15 meters per second. Okay, so your answer to number 1 should be between 10 and 15 meters per second. Now, number 2 is a similar type deal. He's going to shoot a paintball gun horizontally. Okay, there is no initial vertical velocity. And so it's 14.5 meters away. Okay, 14.5 meters, about be from here to the back of the room, so it's a fairly decent shot. Now, here's what you have to realize. As soon as that ball gets launched, it's going to begin to fall because the gravity mafia is pulling it down. And whether I drop it or I let it fall, it's going to fall the exact same distance in the exact same amount of time. So with this one, you can figure out, you know, range equals Vx time. So you know how far it's going to go. You know how fast it's going. So you know your Vx. So then you can figure out, oh, how long is it in the air? Once you figure out how long it's in the air, then you can do 1/2 AT squared plus V naught time. Now, here's what I see where this goes south most often, is that you get that Vx and or that 56.3 meters per second, and you try and put it in there as that initial velocity. Okay? No, this is your mantra. What happens in the x stays in the x. What happens in the y stays in that y. So that 56.3 is that horizontal velocity. That is not the initial velocity that goes into there. Anyway, so your answer to number 2 should be between 0 and 0.5 meters. Okay, it's not going to fall very far because it's not in the air for very long. Okay, when you get to problem number 3, and I promise you there's going to be a problem like number 3 on the test, you mark my words, okay? So we're going to launch this at 47.8 meters per second at an angle of 38 degrees. So Carson, what's the first thing I'm going to do with that launch velocity and that angle?
Cosine and sine.
Beautiful. I need to find my Vy and I find my Vx. And then I never speak of that 47.8 meters per second again. Okay? Don't use it in any way, shape, or form. It is a gateway to get you Vy and get you Vx. And then never use the 47.8 again. Stop. Don't use it. Okay? So, because if your time is wrong, everything is going to be wrong. So if you look at this in terms of Vy, which is about 29.4 meters per second, okay? Now at this point in your esteemed physics career, you should be able to look at that number and go, okay, 29.4 meters per second. That's about 30 if I round it up, okay? It's going to start at 30. So on my velocity time graph, and yes, there's going to be questions about velocity time graphs. So this thing is going to start at about 30 meters per second. And again, it's only the vertical component of the velocity that is impacted by gravity. Okay, the horizontal has nothing to do with it. The overall launch velocity has nothing to do with it. It is only the vertical component of that velocity. Don't talk about Vx, don't talk about the overall launch. Only the vertical. So basically what I'm saying is this. This is an old school acceleration problem. Hey, I'm going to launch something at about 30 meters per second. Acceleration due to gravity is about 10. It's going to take me about 3 seconds. So on a ballpark estimate, my time up is going to be about 3 seconds. Okay? It's like you go to the mall, you have $30. Mom and dad say you have to spend $10 every second that you're at the mall. Oh, I got 30 bucks. Oh, I'm going to be at 20, I'm going to be at 10, I'm going to run out of money after about 3 seconds. So if you like the money analogy, go with the money analogy. So, you know, V equals V naught plus AT, you know, your initial velocity, your final velocity, your acceleration. So that's going to be at about 3 seconds. Oddly enough, it does work out to be exactly 3 seconds. So your total time is 6 seconds. Because if that's wrong, everything is going to be wrong. Okay? So your total time on number 3 is 6 seconds. Okay? And that is a calculation you should be able to do without any hesitation at all. Oh yeah, initial velocity, max height. Velocity goes to 0. I know my acceleration, boom, I'm off to the races. So your max height should be in the mid-40s, and your range should be around 230. Okay? Those are all kind of issues. But your max height should be in the mid-40s, your range should be around 230. And that's a pretty decent shot, the 230 meters. That's like 2 1/3 football fields long. Okay? So that's a pretty good shot on paintball. So when you get to number 4, the only way that you can work number 4 is to do 1/2 AT squared plus V naught time. Okay, that's the only way you can do number 4. Now, here's the story. Your maximum height is about 44 meters, okay? There's 2 ways you can find your maximum height. To get that maximum height, you could use V squared equals V naught squared plus 2AD. That's what I would do because it's not dependent upon time. Take my initial vertical velocity, square that, divide by 2A, boom, I'm off to the races, okay? The other thing that you could do is that you could use this equation. Make sure when you use this equation that that's a negative 9.8 meters per second squared, okay? This is the only way that works is if that's a negative value. Otherwise, you're adding 2 positive values and you get an answer that's way too big. So you've got your initial vertical velocity at 29.4 meters per second. Do not plug in the Vx. Do not plug in that overall launch velocity. Okay, it is only the vertical component that's affected by the gravity mafia. That's it. Okay, it is only the vertical velocity. So there's 2 ways you can find the maximum height. You can use that equation. It's a valid option. Okay, that's what, when I worked it out, that's what I did. I used that equation because I don't like using time. The other option is that you could use time of 3 seconds because that's when you're going to be at your maximum height, which is halfway through the flight. So, you know the 3 seconds, you know your initial velocity is 29.4, plug in the 3 seconds, boom, there you go. Now, let's say you make a mistake. You go, oh, I'm going to plug in all 6 seconds. Well, if you plug in 6 seconds, you're just going to get 0 because at 6 seconds, it's back on the ground. Okay? So if you do make a mistake and you use the total time, oh man, why did I get 0? Oh, that's because that's when it's going to be hitting back on the ground, and that's why I got an answer of 0. So on number 4, obviously your answers have to be less than the maximum height, okay? Because your maximum height is about 44. So if your answers to number 4 are above 44, it's not possible because you already know the maximum height, okay? So it has to be less than that. So both of your answers on number 4 should be in the 30-meter range, okay? Something in that 30-meter range. You're just going to come in here and plug in those times, 29.4, the acceleration is negative 9.8. Now, when you get to number 5, here's Bubba shooting this gun, and here's the paintball, and that's 220 meters away, and this thing is 2.40 meters tall. So what you're trying to figure out is the paintball high enough to clear the wall, okay? That's the $1 million question. Well, you know the maximum height is about 44 meters. So clearly, and just look at this problem in its entirety. Oh, okay, well, I've got a fighting chance because maximum height is 44, wall was 2.4 meters tall. at least I have a chance, okay? Now, if the maximum height of that wall had been 54 meters, you're never going to clear it, okay? Because that's bigger than your maximum height. Oh, it's just going to hit the wall because it's less than that. The other thing to look at is that your range, your total range is about 226 meters. Oh, okay. Again, at least I have a fighting shot to clear the wall because my range is 226. That's ground to ground. So again, look at this and go, oh, right. At least I have a chance. If your range had been 218 meters, you would have never cleared the wall because of the fact that it would never even make it to the wall. What's your range? 218. How far is the wall? 220? Not happening. You're not going to clear the wall, okay? Not going to happen. So this is why you don't just don't get wrapped up in numbers, okay? Look at these numbers in their entirety and go, oh, how does this all fit together? Now, so here's the story. You know your Vx, which is 37.7 meters per second, okay? You know what your Vx is. This thing is 220 meters away. So if you look at range equals Vx time, you know it has to travel 220 meters. That's how far it has to go. You know it's going to travel at 37.7 meters per second. That's your Vx. So then you can figure out how long it's going to take to get there, okay? Which obviously has to be less than 6 seconds because 6 seconds is the entire time, okay? So you can figure out how long it's going to be in the air. Okay, cool. Once you get that number, then slam that back into this equation. So number 5 ends up being just like number 4. You just have to do the added step of figuring out the time. Okay, so that's why I had you do number 4 first and say, oh, okay, right. You can plug in different values of time and find the height. So then when you get to number 5, once you find the time, then it becomes just like number 4, and you slam that into that function equation, okay? So what you should see is that your answer should be above 2.4 meters, okay? Not a whole lot, okay? But you should see that it clears the wall. All right, so you get an answer of about 4.5 meters. Okay, now, on number 6, now we're going to take this through its entirety. So number 6 is like this big culminating problem. So here's the wall, and we want to figure out how far back we can be to shoot the paintball, and it's just going to clear the wall. Now, think this through. When we were at 220 meters away, we were above the wall, okay? So my answer has to be more than 220 meters, because at 220 meters, I was about 4.5 meters above the wall. So I know this has to be greater than 220 meters. But it has to be less than my maximum range of 226. Because at 220, if I was 226 meters away, the ball would just land right at the base of the wall. So this is why I don't want you to just get wrapped up into equations. I'm gonna do equations. I'm gonna do physics. I'm gonna do math. No, stop. No, okay? Think through the problem. Right, 226. 226 is going to land at the base. 220, I'm above it. My answer has to be somewhere between 220 and 226. Okay, so right away I know the range of my answer. Okay? So, here's the simplest thing to do. You know how long it takes to get to its maximum height. That's 3 seconds. Okay? You already have that number. Okay? Now, the tricky part is that you have to figure out how long it takes for it to fall. Now, if it fell all the way down, if it fell all the way to the ground, that would take 3 seconds. Okay, so my time down has to be less than 3 seconds. Again, think through the problem. Right, if it falls for 3 seconds, it's going to hit the ground. I don't want it to fall all the way down to the ground. But here's the kicker. You've hit its maximum height. okay, you're starting to fall. It's like a lemming problem at this point because you're at its maximum height. So, hey, when that thing starts to fall, you're at its maximum height. It's going to start to fall. What's your initial vertical velocity? Zero. It's goose egg. Okay, you have no initial vertical velocity. Okay, so then you can go, oh, right. Distance equals 1/2 at squared plus v naught time. So on the way down, it's a lemming problem. It's going to start at 0. You don't have to worry about that part of it. I know my acceleration. Now, the distance is what you have to think through. Okay? So your maximum height is about 44 meters. Okay? My maximum height. But it's not going to fall all the way from 44 meters down to the ground. It's going to fall from 44 meters down to 2.4 meters. So if it falls from 44 down to 2.4 meters, how can you figure out how far it has to fall? Jack, what are you going to do?
Subtract the 2.
Yeah. So you're going to take 44, your maximum height, okay, what you have is your maximum height, subtract the 2.4, okay, because it's not going to fall all the way down to the ground, and the difference between these two, so that's going to be your max height minus 2.4 meters. That's how far it has to fall. On the way down, your initial velocity is 0. You don't have to worry about that. You know your acceleration. Solve for time. So, oddly enough, your answer to number 6 is somewhere between 220 and 226. Okay? About halfway in between the two numbers, actually. So, there you go. Any other questions on the assignment? If you want to hold on to that and hand that in tomorrow, you can. Okay? Derek, what was that?
We did it a slightly different way, but got a similar answer. Because when I did it, I was like, okay, I was trying to figure out the time.
Yeah.
Was, and so I found the velocity of the paintball right as it goes over it.
Yeah.
And then I used that to find the time.
That works too.
Yeah.
It's a convoluted way, but you
Yeah.
got there. Yeah. Now, if you're really into being a math nerd, okay, then you have to be a hardcore math nerd. Here's the other way that you can do it. You can do it in one step, but you have to use the quadratic. So if you look at distance equals 1/2 at squared plus v naught time. Okay, here's the other way that you can do this, is that you know it wants to be at a height of 2.4 meters. And then you have 1/2 negative 9.8 meters per second squared times t squared plus whatever that, plus 29.4 meters per second times time. So the other thing that you could do is, because you're trying to find, it's a function equation, and you're trying to find the time, okay? So you could just start with this function equation, plug in 2.4 meters, but you can do this in one step, but you have to solve this as a quadratic. So you'd have to get all your numbers on one side, and then you'd have to use the quadratic formula of negative b plus or minus the square root of b squared minus 4ac all over 2a, okay? So you could do it in one step, and you'd get two possible solutions. One number doesn't make any sense because it would be like negative time, which would be really cool, but not going to happen. And then the positive time would be your root term. So you get the time that way, and then plug that into range equals Vx time. So that's the other way that you can do it, is solve it as a quadratic. But you have to be really hard, of course. Like, oh man, Bergkamp, I love quadratic. Good for you, nerd. Okay. Anyway, we're good. Once, twice, sold. Got it? Okay. So let's talk about the final tomorrow. So y'all have been my students for a while now. The finals are going to be all multiple choice. Okay? That could also include like some true-false statements. Like I might give you a statement that says, the longer an object falls, the faster it accelerates. So if I gave you that statement, the longer an object falls, the faster it accelerates. Is that statement true or false? Connor?
False.
Why?
The acceleration stays the same.
Yeah, your acceleration remains constant. In reality, because we have air resistance, in reality, your acceleration actually becomes less because you hit what's called terminal velocity, which if you ever go parachuting, that's kind of a key thing to understand, okay? So in reality, your acceleration actually becomes less. So, but we always assume that it remains constant because that just makes the math work out easier. So if you were me, allowing for everything that you have studied, if you were writing this final, Jack, what would be one type of problem you would put on the final?
Projectile.
Yeah, okay? And there's going to be a projectile motion problem. And there's two types of projectile motions. I'm going to give you one problem where you're going to launch it at an angle, and you're going to have another one where it's going to go flying off a cliff. If you hand in the test tomorrow and you haven't worked one of each type of problem like this, you have done something wrong, okay? Mr. Fisher, if you were writing this test, what else would you put on there?
Probably something about velocity time graphs.
Yeah, okay? So let's say that it's a velocity time graph. And let's say I gave you a velocity time graph that looks like this. And asked you, how many times did that thing change direction? So this is a velocity time graph. There's 0 meters per second. Did the velocity change? Did the velocity change sign twice or once? Once. So this thing only changed direction one time. Because what are the three things that you have to do to change direction? Slow down.
Go from 0.
Go to 0, speed back up. And the only time that happened is right here, okay? I did not change direction right there because of the fact that all I did is I went from positive acceleration to negative acceleration. Now, did my net force change sign? Did my net force change sign?
Yes.
Yes, because remember, only net force equals mass times acceleration. So I went from a positive acceleration to a negative acceleration. The only way that can happen is if I change the sign of my net force. So if you look at this in terms of your car, okay, let's say, for example, you're defining forward as being positive. Doesn't make any difference. Let's say Jack's an optimistic kind of guy. Jack's gonna go, hey, I want positive to be forward. Fine, okay? So what happened is that Jack was already moving because he already has a positive velocity. So Jack was speeding up. So Jack was hitting the gas pedal. Jack had a positive net force and he was creating a positive acceleration. Now, at this point, Jack begins to slow down. So Jack, what did you do at that point?
I start pressing the brake.
Yeah, Jack hit the brakes, okay? Right? Jack hit the brakes. So he went from having a positive net force to having a negative net force. So the only way you can change the slope of a velocity time graph is to change the acceleration. The only way you can change the acceleration is by changing the net force. Okay, so Jack went from hitting the gas to hitting the brake. Now, when it crosses through 0, Bailey Martin, you have a velocity time graph that crosses through 0. What happens when that thing crosses through 0? What do you do? Change direction. So Jack realizes, man, I left my flannel shirt back at home. So Jack had left home, was driving down the road, realizes, oh man, it's Flannel Thursday. I'm taking my midterm final. I have to wear my flannel shirt or Burkamp is just going to I can't take the test. I got to have my flannel shirt. So Jack stops, hits the brakes, slows down, stops, starts to speed back up. So in this situation, he is speeding up because now he's going to have negative velocity negative acceleration, and then he's going to start to speed up. On a velocity time graph, if you were to find that area right in there, what does the area underneath the velocity time graph give you?
Displacement.
Displacement. That's how far Jack went. So if we found that area, we would know that's how far Jack is going to go, because that's what that area represents. Position time graphs. You have the football curve, or the lip curve, A, B, or C. Emlyn Cole, what's the difference between A and C? Which one shows you speeding up and which one shows you slowing down?
C is speeding up
How do you know?
because like the curve's getting steeper.
Yeah, okay. So C shows an object speeding up because the line is becoming more steep. You draw tangent lines, those lines are becoming more steep. No, I'm not going to expect you to draw tangent lines tomorrow, okay? Might have to know the concept, but I'm not going to actually have you actually draw the tangent lines. So C is speeding up, A is slowing down. What is B showing? That's that straight sloping line on the position time graph. Constant velocity, okay? So know how constant velocity shows up on a position time graph and how constant velocity shows up on a velocity time graph. One is a straight sloping line, the other one is a horizontal line. Let's say that you have a velocity time graph and you have a horizontal line at, say, 20 meters per second on your velocity time graph. What does that mean in terms of acceleration? Devon, Wichita wind. You have a horizontal line on a velocity time graph. What does that tell you about the sum of all the forces acting on the system?
There's no acceleration, so they cancel each other out.
So the sum of all the forces is going to equal
0.
0. Okay? So there's two ways that you can do that. You can have all the forces add up to equal to 0. So like, for example, I take this and I push this along at a constant velocity. So if option number 1, I push it along, constant velocity, boom, all the forces add up to equal to 0. The other option is that I throw it and there's just no forces acting on it, and the inertia will keep it moving at a constant speed. Okay? So there's two ways you can have constant velocity. Forces balance out, or there's just no forces acting on the system at all. Okay. Promise you there's going to be a problem like this. Here's the pulley. And you're going to have masses suspended over the end of the pulleys, right? So let's make the math easy. Let's say this is, I don't know, a half a kilogram. And let's say that is also a half a kilogram. Okay? Make the math easy. So let's look at two scenarios. Scenario number 1, let's just look at all the forces acting on the system. So I have a half a kilogram mass suspended in the Earth's gravity. Jaden, how am I going to calculate the force acting on a half a kilogram mass?
Take the mass times gravity.
How about my gravitational acceleration? How about that? It's literally worked out to mass times gravity. Okay, but I know what you meant. How about by 9.8 meters per second squared? And we're going to get 4.9 newtons. Okay? That is the only force available to make the system move. Okay? That's it, nothing else. So we're going to look at some different scenarios. Scenario number 1, we have a 4.9 Newton force. Go away. And I cut the string. Just sever it. Okay? Cut the string. It's gone. Jaden doesn't have to take along her little brother. I cut the string. What's going to be the acceleration of that 1/2 kilogram mass? Jaden.
1.8 meters per
Thank God you didn't say gravity or I would have flipped out. Okay, so the acceleration due to gravity is going to be 9.8 meters per second squared because I have a 1/2 kilogram mass. That's acted on by 4.9 newtons. I take 4.9 newtons, I divide that by the mass, I'm going to get an acceleration of 9.8 meters per second squared. Now, situation number two. Situation number two is that we don't cut the string, but Jaden has to drag along her little brother. Okay, so Jaden's gone out on the date. Mom and Dad said, hey, you got to take along your little brother. Jaden's going, oh, really? Okay, so when Jaden takes along her little brother, what's that going to do to that 4.9 Newton force? Izzy. When she drags along her little brother, is that going to change the gravitational pull acting on that mass?
No.
It's the exact same, okay? Jaden still has the exact same desire to go out on her date, okay? Same force that she wants to go out. Boom, right? But now she has to drag along her little brother. So what's going to happen to her acceleration? Jaden, what's going to happen to your acceleration? Is it going to be bigger or smaller than 9.8 meters per second squared?
Smaller.
Smaller. Now, so force net, oddly enough, equals mass times acceleration. My net force is still 4.9 newtons. But now, I have to divide by the total mass of the system. Total mass of the system. So what's the total mass of the system? I got 0.5 and 0.5. Check my math, but that adds up to 1 kilogram. So now I have a 4.9 Newton force acting on 1 kilogram. Divide that by 1, I should get, unless things have changed, 4.9 meters per second squared. Ah, right, cool. So let's look at the graph. This is mass on the table, and this is the acceleration of the system. Okay? So there's 0 mass, and there's, let's say, 1 kilogram. Okay? So, situation number 1, this is the mass that's being pulled down, 1/2 kilogram, right? So if I have no mass up on the table, what's the acceleration of the system going to be? There's no mass up there. We just take the 1/2 kilogram mass like this, boom, we just drop it. What's the acceleration going to be? 9.8 meters per second squared, right? Okay? Now there's nothing up there. There's no mass up there on the table, right? Now, what we just figured out, if the mass up there on the table was 1/2 kilogram, the acceleration is going to be 4.9 meters per second squared. So, as I increase the mass of the table, what's going to happen to the acceleration of the system? Bailey Martin. I put more and more mass up there on the table. What's going to happen to the acceleration of the system?
It will increase. No, wait, say that again.
Okay. I'm going to put more and more mass up on the table. Jaden is going to have not only take her little brother, now she has to take her little brother's friends. Horrible. So what's going to happen to Jaden's acceleration?
Oh, want to say the same? Wait, I'm so confused.
Okay. Visualize this. We're going to visualize this, Jaden. Okay, so here's Jaden. She wants to go out on her date, right?
Yeah.
So there's 1/2 kilogram. So Jaden's desire to go out on the date is a 4.9. Okay? Not a 5-star, 4.9. The date isn't a 5-star, but it's really close. It's a 4.9 star. Okay? It's not bad. Okay? Right? So if Jaden is just going out on her date, all of that force goes to accelerate Jaden 1/2 kilogram. We get an acceleration of 9.8 meters per second squared. Okay? No, there's no mass up there. No mass. Now, as I put more and more mass up there that she has to drag, what's going to happen to her acceleration? Will it increase, decrease, or stay the same? Yeah, because look what's happening. I'm going to divide by 4.9 newtons by a bigger and bigger and bigger mass. There's more inertia. There's more stuff to move. There's more resistance to that acceleration. So on this graph, as I increase the mass on the table, this graph is going to go down like this. As I put more and more mass up on the table, the acceleration is going to become less and less and less because it's the same applied force acting on more mass. I get a smaller acceleration. Okay? Now, scenario number 2. There was friction up there. There's friction between the block and the table. Now what's going to happen to her acceleration? Bigger or smaller than without friction? Smaller. Okay? So now, not only does Jaden have to take along her little brother's going, I don't want to go. Okay? And he's like, got his feet and he's hunkered down. He's like this, no. Okay? So now Jaden has to drag her little brother with her. Okay? Now her acceleration is really going to tank because not only does she have to drag her little brother, the little brother doesn't want to go. He's like, girl, you can't make me go. Okay? And so now she has the same desire to go, 4.9 stars. Okay? But now it's really going to be tough for her to accelerate because not only does she have to take her brother, the brother doesn't want to go, and there's friction. Okay? All right. Situation number 3. Now we're going to put Jaden on an incline. Sorry, Jaden. Okay? So we're going to put Jaden on an incline. Oh, incline planes. What are the 3 forces that are always present on any inclined plane? Peyton, what's one of them?
Force parallel.
Force parallel, which always acts which way?
Down.
Down the inclined plane. And force parallel, remember, equals FG sine theta. Always acts down the inclined plane. That force parallel is never going to push you up the hill, ever. It's always going to act down. Miss Elliott, what's another one?
Force gravity.
Which always acts straight down. And that's just mg, okay? Basic run-of-the-mill thing. It's just mg. So what's the third one?
Force normal.
Force normal. And force normal is Fg cosine theta. Do not forget the cosine theta part of this. And also, Dora, make sure when you come into this room, make sure your calculator is not in radian mode. Make sure that it's in degree mode so you don't get weird answers that don't make any sense. Okay, so here's an interesting thought. Let's look at this graph. So this is, we're going to look at acceleration. And this is going to be the angle. Okay? So here's 0 degrees. And here's like, say, 60 degrees. Okay? So imagine this. We have a 1/2 kilogram mass up here, and we have a 1/2 kilogram mass here. Let's assume that there's no friction. Okay, so let's leave friction out of this. So we said if both of those were 1/2 kilogram, okay, we would get an acceleration of 4.9 meters per second squared. That's just flat, okay? 4.9 newtons acting on 1 kilogram, we're going to get 4.9 meters per second. Okay? Now, as I increase this angle, okay, so imagine I start to lift this thing up. She's still being pulled down. What's that graph going to look like? So as the angle gets steeper, what's going to happen to that acceleration? It will it increase, decrease, or stay the same? Become less. Why will it become less?
Because force parallel is stronger.
Yeah, so force parallel is, gravity mafia is getting stronger and stronger and stronger, right? So this graph is going to start to go down here like this. Now, eventually, that force parallel could equal the weight pulling down. Okay? So if that ever happened, then you would have an acceleration of 0. So as the angle gets steeper, your acceleration is going to become less because you have more and more force pulling you down. Okay. Atwood machine. Okay? By an Atwood machine, I mean that system where you have one pulley. Okay? And let's say that I have a 0.5 kilogram mass over here, and I have a 0.6 kilogram mass on this side. Okay? So I have a 0.6 and I have a 0.5. Okay? 0.6, 0.5. Mr. Fisher, which one's going to fall?
It's gonna be the 0.6 kilogram one.
So if I take 0.6 times G, I get about 6 newtons. Round number, I get about 6 newtons. 0.5, I get about 5 newtons. Okay? So I have a 6 Newton force pulling down on one side and a 5 Newton force on the other. So here's Jaden's desire to go out on the gate, 6 newtons. Has to take little brother. Little brother's going, I don't want to go. 5 Newton opposing force. 6 Newton, 5 newtons. What's my net force going to be? Do not make this difficult.
1.1 kilogram.
No. It's going to be 1, but not 1 kilogram.
1
1 Newton. Okay? We're not doing Devon, can't win Wichita physics. We're going to put units on stuff. Okay? Okay? So my net force is going to be 1 Newton. But to get the acceleration, what am I going to divide by? 0.5, 0.6, or 1.1 kilograms? 1.1 kilograms, you always divide the net force by the total mass of the system. Speaking of net forces, what are the odds that you're going to have a rocket problem on this final tomorrow? 100%. Okay? Here's how this is going to play out. Somebody had asked me about this earlier. I'm going to say, here's the mass of the rocket. I'm going to make a number, let's say it's 5 kilograms. And I'm going to tell you that the upward force from the rocket engines is 100 newtons. Keep in mind this is multiple choice. Okay, it's going to be a multiple choice problem. Okay? I'm going to say the rocket is being launched straight up. You have an applied force of 100 newtons. The mass of the rocket is 5 kilograms. And I'm going to ask you, what is the acceleration of the rocket? And what do you think you will do wrong? And what's going to be a choice on this test? What are you going to do wrong? Who are you not going to pay?
Gravity mafia.
You are not going to pay the gravity mafia. You go, oh, Burkamp, I got this. Simple. F equals ma. Here's my force, 100 newtons. Mass is 5 kilograms. I'm going to take 100 and divide that by 5, and I'm going to get 20 meters per second squared. And that's going to be choice A. Easy. Got this. It's not a problem. What physics? What? 100 newtons divided by 5, 20. Is that the correct answer? No. What did you not do? Pay the gravity mafia. How much does the gravity mafia charge per kilogram? $9.80. You have $9.80 that you have to pay the gravity mafia per kilogram. You have 5 kilograms, 5 times 9.8. You have to pay them 49 newtons. So of the $100 that you have, you got a crisp $100 bill. How much of that do you have to give to the gravity mafia? 49. What do you have left? 51 newtons. Divide that by the 5 kilograms. Boom. There's your acceleration. That would be choice B. Okay? Something like that, right? Because I do know every mistake that you will make. And if you make that mistake, that answer is there. Yes, I'm a jerk when I write my physics or when I write my multiple choice. Okay? It isn't like, 20, 1,000, 5,000, and then the speed of light. No. No. So just keep that in mind. I promise you I promise you, this is gonna be at the, I'll tell you where it's gonna, bottom of the front page. Devin is going to launch a water balloon at a certain angle, and it's going to go like this. Okay, it's going to be a series of multiple choice questions. I'm going to give you that launch velocity, I don't know, say 40 meters per second at an angle of 30 degrees. And I'm going to ask you to calculate a whole bunch of different things. And that might be 20 meters above the ground. So imagine this. Here's Devin launching a water balloon 20 meters above the ground, okay, at an angle of 30 degrees with a velocity of 40 meters per second. What's the first thing that you're going to do with that 40 meters per second? Gateway into Vy and Vx, okay? Vy and Vx, that's your gateway equation. Are you ever going to use the 40 meters per second again? No, okay? So, I promise you, there's going to be a problem like this, okay? It's going to be at the bottom of the front page. I'm going to tell you right now, Devin is going to launch the object, okay? So look for the Devin question, okay? Devin is going to be on the problem. So when you see Devin, you think, ooh, Vx, Vy, okay? I'm telling you, Devin is going to launch the balloon. It's going to be at the bottom of the front page. Look for the Devin problem, okay? All right. Let me see. Those are the big things that are on it. Okay, so I'm going to stop. So here's what you've got. As usual, you're going to have a blank review. Then you have the answer keys to it, okay? I also have all of your tests. If you, and you're in files, if you want to go back and spend this time looking at the old tests, you can do that, okay? Make sure that you know terminology, precision, accuracy, independent variable, dependent variable. Force equals mass times acceleration. What does that look like on a graph? Okay, if you were to plot force, mass, acceleration. Oh, force, that's my independent variable. Oh, that's going to go here. Here's my acceleration. Oh, that's going to be a linear function. Oh, what does the slope represent? 1 over kilograms. Okay, that type of thing. So it is funny. You go back and you look at the first test and you think, wow, how did I miss anything on those questions? Okay, so it's kind of cool to go back and look where we started and where you are right now. So how you use the time is up to you. If you want to work on the review, work on the review. If you want to scour through your old tests and find problems like this, for example, what I would recommend is that on that big acceleration test, you had the ball off the building problem, okay? That's basically what Devin's the Devin problem is gonna be a ball off the building problem. The only difference is that I'm gonna make it a projectile motion problem, okay? But once you find your Vy component, then it's just like a ball off of the building problem, okay? So I'd go back and look at that. Your forces test, okay? You just had that, that's in there. So anyway, how you use your time is up to you. I'm done. If you want to look at your old tests, no, you can't take your tests with you, but if you want to look at those tests in your folders, you can. So stop that. I'll hand out the review.